Right, so lots of challenges involved in this. So welcome back. So first of all, the problem is inherently relational. There are many types of objects, for example, patients, body parts, tests, infections, and relations. There's relational uncertainty, which means we don't know what's true about the world. There's identity uncertainty. We don't know whether whether two descriptions refer to the same object or for different objects. And existence uncertainty. We don't know what exists. We need to interact with standardized vocabulary. SNOMED CT is a large medical vocabulary that contains 350,000 medical concepts in multiple languages. So there's basically for everything that doctors observe or write down electronic health records, there's a description in SNOMED about what it means. Now it turns out that there's approximately 100,000 what are called clinical findings, which we can consider as symptoms in there. And 100,000 is interesting because the number of pairs of 100,000 is approximately equal to the population of Earth, the number of people on Earth. And because most of these are very rare, quite rare, for almost every pair of the symptoms, or every pair of disease, or every disease treatment pair, no one in the world has both. So it's inherently, there's just not enough, there's just so many pairs of diseases, symptoms, or pairs of disease symptoms pairs, there aren't enough people to go around to actually show these. So inherently we cannot learn these from data. We need to go from somewhere else. We need to understand a bit more about what's going on. There is, however, lots of expert and textbook knowledge. It sometimes is wrong, it sometimes oversimplifies things, but it's much better than using nothing. So people know lots of things because they've observed lots of data. We've had lots of historical data and people have built up knowledge about the world. But sometimes can't just treat it as gospel truth. We want to use whatever evidence we can get to learn from. Current electronic health records are terrible. I'm told that what happens is that the doctor either gets paid for symptoms or diseases in a lot of these cases, and they get whichever is paid less. So they never write down the symptoms or the disease. They write down whichever one gets paid, which gets paid the most. So there's inherent bias in order to not collect good data, which is sort of very surprising. We need to justify recommendations. People don't just believe things because we don't just believe things just because someone tells us something. We need to justify recommendations. And we always want to base decisions on the best available evidence. Another challenge is transportability. We want to learn in Vancouver and apply it in Beijing. So we need to explicitly worry about, we don't necessarily apply it in the same place we've done it. We're not necessarily applying data in the same place that we found it. So we can't assume they have the same distribution of values. All right. And there's a real challenge in here. So in medicine, there's something called PubMed, which is basically a collection of all articles published on medicine. It has about 29 million citations for biomedical literature, and 10,000 are added each week. So 10,000 articles on medicine means no one can even read a tiny fraction of the articles that are published. So no one's up to date with all the latest medical research. So IBM Watson and others have proposed to read the literature to provide evidence-based advice for specific patients. And what I want you to think about is, can we do better than starting from the data, which the doctors and the scientists who write the papers do? Then they make hypotheses and fit them to data, and then they get this. And then they put that together in a research paper. And then IBM tries to read this research paper and then applies it to clinical practice. I mean, the trouble with this is, of course, this going from research paper to misreading is actually misreading the research paper, not getting it right. We need to understand a lot more about the meaning of the research papers. So the proposal is wouldn't it be better to have the research published in machine readable form instead of just extracting it from the English? So in geology is also interesting because geologists know they need to make decisions under uncertainty. For most geological phenomena, you can't actually accurately predict when landslides are. You can't accurately predict where you'll find some mineral or something else. And in fact, it's so hard to predict that for almost all mineral deposits, when people are exploring for minerals, they have a 99.9% failure rate. There's only 1 in 1,000 explorations that people pay lots of money for that actually end up with something valuable. So the geologists know they need ontologies. We know that geology doesn't change at arbitrary political boundaries, but when different jurisdictions have put in their own vocabulary, then the maps show the political boundaries. So it becomes pretty clear that you need to standardize the vocabulary so everyone means the same thing, so that it doesn't depend on the political situation. So it turns out that lots of observations are published by geological surveys of countries or states and provinces and globally. And so there's some of them is actually got from satellite imagery, so we get that. But there's also lots of observations of the ground, rock type, what's underneath the rocks, depth of soil, all sorts of information that are relevant to geology that are published by geological surveys. The geological hypotheses are published in research journals, so they're actually publishing hypotheses about the world. And work with Clinton Smythe of Minerva Intelligence, what's currently Minerva Intelligence, as we built systems for mineral exploration and landslide prediction. We represent the hundreds of hypotheses of research papers and match them on thousands of descriptions. So the general goal is that we want to have people publishing hypotheses about the world. We want to represent them in machine readable form and map them all over the world. It's actually more challenging than you might think. So one of the examples of doing this is Geology is a place of where people report, which publishes the geology of the world. So here's an example of one of the Canary Islands. If you notice the scale here, there's about 12 kilometers across, and this is about the detail that they put in the geology of the world. So this one here is the different colors here are the different rock types, I think. And so what's happening here is that there's this much detail about the whole world we can use for making predictions. So what we're going to do is we're going to look at this picture here. So we're going to start off with ontologies that represent the meaning of symbols. So we need to define the vocabulary we're going to use. Then observational data describes the world using the symbols, so that we only have the data when we know what things mean. So otherwise it's just a meaningless set of bits, but we need meanings associated with them to make this data useful. Then we make hypotheses. They're just going to be programs that make predictions on data. We take some training data, and they have to use the vocabulary of the ontology in order so we can understand what they're predicting. And data is then also used to evaluate the hypotheses. And hypotheses are then used for predictions in new cases, and so now we can make predictions about what patients, what might have wrong with them, or predict where we might find a particular mineral, or predict landslides. And all of these evolve in time. Okay, so that's the idea about what we're going to do. We're going to think about this diagram here.